Good morning, everyone. Okay, we'll start in just a minute. Yeah. Okay, before we start, if anyone has any questions. Anything you want to ask? Okay, there are two people only. Let's wait for maybe 2 more minutes and then we'll start. Okay, let's start regardless. I mean, doesn't seem like other people would join in. Okay, we are trying to continue from the last topic that we were discussing, which was logistic regression and SVMs. So the SVMs I'll cover in detail at the end of the course, in the last few lectures. So these were your binary classifiers. What we'll do is, we will see how to apply these binary classifiers for multi-class datasets. So today we are going to discuss these strategies, which are called as meta strategies or extension strategies. So we will see how to apply any binary classifier, okay, onto multi-class datasets. Okay. Now, for multi-class classifiers, there is no need because you don't need these strategies. But if a classifier is binary by nature, you would need these strategies for you to leverage the capabilities of a binary classifier on multi-class. Okay. So let's see with a small example, and there are many meta strategies. So let's see the differences between them. So I'm going to draw maybe say a multi-class data set. First, let me create a small table to illustrate. So imagine we have two features. Okay. So on the basis of, okay, say two features, I'm going to figure out, let's say if the person is, say obese, say healthy, or underweight. So this is what I'm going to figure out. Okay. So let's say obese is class 1. This is class 2. Okay, and this is class 3. So you can see that I have a multi-class data set. Okay. Since I have more than 2 classes. Okay, imagine feature 1 as your age and feature 2 is say height. Okay, you can put weight also, it depends. Okay, so this is these are 2 features. So let's say the data looks like this. Okay, so just for simplicity's sake, let's try to understand it. Okay, let's say the age is 10, height is 20. I'm just imagining some random numbers. So the person is maybe say underweight. Okay, and if this is 12, and if this is maybe say 22, this is class 3. Okay, so let's say underweight I'm representing with triangles. So if something is a 3, then I'm going to represent it with a triangle. So this is your age, this is your height. So this is your feature x2, this is your feature x1. So this person 10, 20 is going to be somewhere here. Okay, let's say this is 10 and this is 20. Okay, so this triangle is somewhere here. I'm representing it with a triangle just to show that, okay, this person is underweight. Okay. Similarly, this is 12, 22, which would be somewhere here. Does this make sense so far?
Yes.
So far, so good. Okay.
Yeah.
All right. Now, so let's say these class 2 people are maybe say squares. These two class 2 people are squares. Okay. So let's say there is another person whose age is say 14. Okay, and maybe say this is 23. So this guy is class 2. So 14, 23 would be somewhere here. So this is class 12. Okay. And let's say 16, say 28. So this is also class 2. So maybe this is somewhere here. Okay. And finally, we have some people with class 1. Let's say these are okay, circles. I'm representing them with the circles, not a 0, but with a circle. Okay, let's say this is 18, maybe like this. Okay, maybe this is say 10, not 10, 10 would be too small. Okay, let's say 18, 34. Okay, let's say this is class 1. So 18, 34 would be this. Let's say here, and 20, say 36, maybe somewhere here. So this is how the data looks like. All right. Now, since we have these 3 classes, do you think if I use a binary classifier like SVMs or logistic regression, is one line going to be sufficient to separate more than 2 classes? Do you think is one line sufficient to separate more than 2 classes?
No.
No, sir.
No, right. Okay. So we need at least 2 lines, right? However, even with 2 lines, there is a problem. Okay, let's think of this. Okay, let's say I draw this line. Okay, I draw this line, and I give you a sample. What do you think? So, okay, what do you think this line will do? Okay, you are saying that I will draw these 2 lines? Yes, sir.
Yes, sir.
Yeah.
And okay, so think about this. When you're going to make a statement, like anything above this line is going to be what?
Going to be healthy and underweight. It's under.
Healthy and underweight, right? So there are 2 things, right? Not one thing. Yes or no?
Yes.
Okay. Now I want you to realize one thing. Which class would typically have more probability? The circles class or the square class for this line L1? Think. Which class out of these 2 will be having more probability for a prediction?
Above ones.
The one which is here, right?
Yeah.
Which is far away. You are much strong in that, right? So don't you think this class will kind of overshadow the square class?
Yes.
Yes.
So whichever prediction that you will get from this line, it will be in favor of that class, right? Not the square class. Does that make sense? Even if this point is here. Yes or no? Similarly, if you think about this line L2, look at the bottom half of this, okay, towards the left of it. What do you think everything will be predicted as? A triangle. No, not square, a triangle, which is like the furthest away. So this square class will be overshadowed by the lines.
One minute, Sanatan. Like the first line will all predict the squares, and then the second
No,
line.
the first line will actually predict it as circles. The first line, if you look at to the right side of it, right, it will predict everything as circles, because when you look at circles, right, you are more confident about them. Yes or no? See, you are trying to make use of 2 lines here, okay? You'll be using 1 line at a time, right?
Yes.
Okay. Okay. Let me just simply ask you this. What do you think one line returns? One line returns a probability value, right?
Yeah.
A real value. Okay. It doesn't return two values. Let's just first argue on that. Okay. So if one line is going to return one value, okay. So first of all, how can we say that there are two classes? I mean, currently we have, can I say these two classes are not triangles? Yes or no? With respect to
Yes.
line L1, if this is triangle, these are not triangles, right?
Yeah.
Amongst the not triangles, which class will dominate?
Repeat your question, please.
Amongst the classes which are saying that they are not triangle, which class would dominate?
Not triangle.
There are two classes right here.
Yeah.
You are looking at with respect to class L1. Which class would dominate amongst these two?
The circle was far away, so I think
Circles
that
will dominate, right?
Yeah,
Because
yeah.
so that class is dominating, right? So if I give you a sample here, what should be the prediction for that amongst the not triangle class? The circles, right?
Yeah, circles.
Anywhere, wherever I give you this point, even if it is here, with respect to line L1, you will always say it is going to be a circle.
Circle, yeah.
Okay. So this square got overshadowed, right? Do you realize that?
Yes, yes.
Okay. Now think for the same for L2. Triangles will now overshadow the squares. So this is say not this is circle class. Can I say these two will be not circles?
Yeah.
And look with respect to now line L2. Can I say that triangles will now overshadow the circles? Because
Yes.
anything to the left of L2 will be classified as a triangle, right? Amongst the circles. Yes or no?
Yeah.
Okay. So two lines are actually not sufficient. So I'm going to show you what is actually done. Okay. You need three lines, not two. Okay.
Okay.
Okay. This concept is actually called as masking. Okay. So what masking does is you can say that some classes, or in this case, one class is being overshadowed by the other two classes. Okay. All right. Let's look at this. Now you know that your binary classifiers can only do difference between two classes, right? Yes or no?
Yes.
Your binary classifiers can distinguish between two classes only, right? So I'm going to show you how to work with that. So the first strategy that we are going to do is called as one versus rest. And what this strategy says, so each of these meta strategies, let me write what they do. Okay. See, you're going to use binary classifiers, keep that in mind. So they will work only on binary data sets. Do you agree with that? Yes or no?
Yes.
I'm going to make a statement. Your binary classifiers will only work with two class data. They will not work with more than two class data. Okay, keep that in mind. So somehow, let's say magically, if I can transform my multi-class data set into binary data sets, okay, do you think then I can apply binary classifiers onto it?
Yes. Which
Now,
means
how
you're
to do
saying
that?
like
Go on.
I'm gonna divide the multi classes, like if I'm having 4 or 5 classes, I'm gonna divide it into 2 and then I'm gonna work on it. That's
Yes.
Okay.
I'm going to magically transform everything into two classes. Okay. And it will not be a single data set anymore. It will be multiple binary data sets. So a single multi-class data set will be converted to multiple binary data sets. And for each multiple data set, right? For each binary data set in the transform data sets, I'm going to use a binary classifier. That's how simple it is. So let's see how to transform. This is the important part. How to transform these multi-class data sets. Okay. So there are many strategies to it. We'll see them one by one. So the first strategy that I'm discussing is one versus rest. Okay. So what this one versus rest strategy says, or rather, let me discuss this easier one first, which is one versus one. This is easier one. What it says is, see, you have three classes right now. Why don't we just look at two of them? Forget the third one. Okay. So it is like this. I'm going to use two classes only at a time. So can you tell me which classes should I consider?
1 and 2 first.
Okay, let's say 1 and 2. So 1 is circles and 2 is squares. Okay, so I'm going to, so this is the same illustration. I'm making it just slightly short. So if this is 1, okay, so if this is your, sorry, 1 is circles, which is here. Okay, and 2 is this, right? Yes or no?
Yes.
You just said 1 versus 2, right? Okay. You just mentioned you want to take 1 versus 2. So 1, as you can see, is circles and 2 is this squares. Okay. So I'm ignoring the triangles. So what are the actual outputs in your logistic regression data set? Can somebody help me recall? With what integer labels do you represent your actual outputs if you are using logistic regression?
0.
0 and 1. So all that you have to do is replace one of the labels. So represent any of the squares by a 0, or you can put it as a 1 and the other one as a 0. Okay. See, what I'm saying is you are going to ignore these class 3 samples. Does that make sense?
Yes.
Ignore these class 3 samples. And since you are doing 1 versus 2, you can assume that one of the classes is a 1 and the other class is a 0. So just replace 1 with a 0 maybe, and maybe say 2 with a 1. Do you see that now I have a binary data set?
Yes.
So basically ignore these samples and you just have a binary data set with 1 versus 2. And now I can use logistic regression to differentiate them. So logistic regression will give me a separator, which I have drawn just to illustrate. So anything above this line is going to be what?
0. Sorry, 1.
It is going to be, whichever class it is. So this is the circles class, right? And what does circles indicate? Obese. Right? Does that make sense? Anything below it is going to be the squares. Squares are healthy. So anything below it would be healthy. Does that make sense? So currently I have just distinguished between healthy and obese. Do you think that I need one more to distinguish between obese and underweight also? I do need that, right? Okay. So maybe say I'm going to distinguish between 1 and 3. Okay. So 1, as you know, is this class, which is circles. And 3 is which class? Which is triangles. So you can, again, ignore the other class. Okay. Ignore the other class. Assume that, so I'm assuming say 1 is 0 and 3 is 1. Okay. I'm relabeling them. Okay. 1 is 0 and 3 is 1. Okay. So anything above it is going to be circles. Anything below it is going to be triangles. Okay. Same thing. Can you do it? So do you require one more? Which combination do you require?
2 versus 3.
2 and 3.
2 versus 3. Okay. So take the second class, which is your healthy class, which is here. And the third class, which is your underweight class, which is here. Okay. And try to draw a separator for that. Okay. Now, I want you to focus on this. So how many models do I have right now? Okay, is there any other combination which I missed out?
No, sir.
No, right? Okay. So I made 3 combinations, right? So 1 versus 2, 2 versus 3, and say 1 versus 3. Okay. So let's say this is model 1, this is model 2, this is model 3. Okay. So each model will have its own thetas. How many thetas will each model have? How many models will each theta? How many thetas will each model have? There are 2 features.
Total 3 thetas. 1 2 will be the coefficients and 1 intercept.
Correct. Let me label it like this. Does that make sense to everyone? Yes or no? I'm going to label it like this. These thetas will be different depending on the data. Okay. So you just need to keep in mind which is 0 and which is 1. So I'm just assuming this is 0 and this is 1. You have to label everything. Okay. All right. So now I have to make a prediction. Please listen to this carefully. So I give you this sample, age and height. So you will have a 2-dimensional sample. Okay. You have a 2-dimensional sample. And the value for this sample is maybe say 20, 36. Okay. So this is the sample that I have, and I want to predict if it is class 1, class 2, class 3. Okay. This is one of the test samples that you have. So how do I predict? So the idea is I'm going to pass this to model 1. Okay. So how does model 1 make a prediction? You will have theta naught plus theta 1 x1 plus theta 2 x2. So you will pass 20 here and 36 here, right? Yes or no?
Yes.
Do you remember I spoke about this? If it is greater than 0, it is which class? If it is greater than 0, it is which class?
One.
If it is equal to 0, it is which class? You don't know. That's a dilemma. If it is greater than 0, it is class 1, otherwise it is class 0. Okay, that is one way to do it. But we are interested in the probability score. How do we get the probability score?
Sigmoid.
Apply the sigmoid on top of it. So you're going to do the sigmoid on top of this. What is the formula for sigmoid? 1 divided by 1 plus e to the power of minus of this entity.
Yes.
Okay, assume that 20 is put in x1 and 36 is put in x2. So this score will be in what range?
0 to 1.
0 to 1. Okay. All right. Now here comes the interesting part. So you're going to get a probability score from this model 1. Let's say this number is 0.3. Assume this number is 0.3. So can I say I'm 30% confident in favor of class 1?
Yes.
What is my class 1 rather?
2.
Okay. So what is your class 2 by the way? I think it's healthy, right? And you're 70% confident that this is class 1, which is, I believe, underweight. You can actually check that. Class 1 is obese, my bad. Class 1 is obese. Okay. All right. Can you repeat the same for this model 2 also? Pass this to model 2, get the probability. Let's say this probability comes down to be 0.65. So can I say that I'm 65% confident that this is class 3, which is underweight? Class 3 is, class 3 is underweight, right? Yeah. So class 3 is underweight. And 35% confident that this is class 2, which is healthy. Okay. And similarly, let's say you pass it to this third model, and let's say this gives me a number 0.78. So 78% confident that this is class 3. Class 3 is underweight. And 22% confident that this is class 1, which is obese. Now you have 6 predictions. How do you predict out of these 6 predictions which class should be assigned? We have 3 models. From these 6 predictions, how do you assign? Any guesses?
Whichever has the highest probability.
That is the answer to this. Assign the one with the maximum. So you have 6 predictions overall, right? 1, 2, and 3. From these, you take the maximum. Okay. Choose the class with the maximum probability. Choose the class with the maximum probability. Okay. So which class should you think we should assign?
3.
3, which is underweight. So this is the first strategy. Do you want me to discuss the bottlenecks of this strategy right away, or maybe a little later when I show you the second as well, and then we can contrast between the two?
Any which ways you feel is better.
Okay, let's discuss the second strategy first. Okay, this is called as one versus rest. Okay. All right, before I discuss this, at least some basic questions. Assume that if you had 4 classes, how many models will you train?
Like you're saying, how many classes
Yeah, so
are I
currently with
classifying?
3 classes, I trained 3 binary models, right? M1, M2, M3. What do you think this number would be if I have 4 classes?
I'll
Five.
I'll classify 4.
Dual
Okay,
model.
so how many?
Dual, I think.
No.
No.
No. This is the IQ question. Okay. Let me ask you this. There are say 4 people in a room. How many handshakes are possible? Unique handshakes, I'm asking.
4 choose 2.
4 choose 2. It's the same concept here. You are going to take pairs. Okay. So what is 4 choose 2? 6. 4, sorry, I'll just mention it. 4 factorial divided by 2 factorial into 4 minus 2 factorial. Okay. 2 factorial is 2. Okay, can just cancel it out. Does this make sense? Yes,
Yes.
people. Should I write it generically? N choose R as n factorial divided by R factorial into n minus R factorial. Okay. Okay. Now, do you want me to write all the 6 combinations? It's pretty easy. Okay, say you will do 1 and 2, 1 and 3, 1 and 4. Okay. Then you will do, see, do you think I need to do 2 and 1 again?
No.
No, right? 2 and 3 and 2 and 4, and then there will be 3 and 4. Do you realize that these are the 6 combinations? Any other combination that I missed? Think. It will already be there. Okay. Is this clear?
Yes.
Yeah.
Okay. So for k classes, this number is k choose 2. So do you think this strategy is advisable when the number of classes are more?
No.
So if we were using this 4 choose 2, so that we don't need to work on the things again, like 2 1 3 1 again, as we have already worked on the
Correct.
classes 1 and 2.
Correct. Correct. So the idea is if you have k classes, then you have to train k choose 2 models. So this is quite expensive. You don't need to do that. Okay. And one of the questions is this. Okay, I'll ask you this and maybe after I discuss one versus rest. So you will see a contrast as well. Okay. So what one versus rest says is this. Okay. It's actually very, very simple. It's the same as 1 versus 1, but subtle differences there. So let's say this is the data set that I have. Okay. I'll just want to ensure that I want the same data set. Okay. Triangles, squares, and circles. Let's say this is how the data set looks like. Okay. Now, 1 versus rest, what it says is this. Okay. Look at this carefully. Do you remember one-hot encoding?
Yes.
Okay, I hope everyone does. Okay, so I'm going to show you the outputs of these classes. Okay, focus on the outputs only. So there are 6 outputs. Okay, and the outputs are 3 3 2 2 1 1. Okay, so assume that I'm going to encode this column output y. Okay, how many columns will you make?
Can be done with 2 columns.
No, but you need all 3 here. You can do it with 2 columns. I don't want to miss anything, but that's the objective. So let's say this is class 3, this is class 2, this is class 1. You can keep it in any order, it doesn't matter. So what will be the first vector?
1 0 0.
1 0 0. I want you to focus on this. Let's say the original data that I have, okay, which is x1 and x2. Okay, use this as your input features, x1 and x2. Okay, and use this encoded output as the first output. Okay, okay, can you interpret it in plain English? What is this vector representing? What are you trying to differentiate? If you were training a model for, say, this output, let's say this is y1. Let's call this as y3, this as y2, and this as y1.
If a output is class 3 or not.
Correct, right? So can you see that it has converted to binary now?
Yes.
And what it is doing class 3 versus
Is rest.
rest. Can I say not class 3?
Yes.
Is rest not class 3, right? So this is class A versus not class A. Okay. So you can see it's binary. Okay. So what it is essentially doing, it is actually doing it like this. Please see to this very, very carefully. So class 3 was which class? Underweight, and I represented it as a triangle. Okay. This was class 3, by the way. This was 2, and this was 1. Okay. So see, when you converted this data set, it is as simple as doing. So your class 3 stays the same. Okay. Your class 3 stays the same. But now you are saying that any other class which is not class 3, you are going to represent it with a special symbol. Let's call it as X. Okay. And now don't you think that I can separate triangles and X's?
Yes.
Okay. So this is not class 3 and this is class 3. Okay. Please remember on what labels binary classifier works, logistic regression works.
0, 1.
1 and 0. So class 3, I'm going to label it as 1, and not class 3, which is rest, is going to be labeled as 0. You can see that I am representing class 0 with the symbol X. Okay. The actual class is represented with the same symbol. So does that make sense?
Yes.
Yes or no? Okay. So this is your model 1, which differentiates class 3 and not class 3. Okay. Same thing. Can you do it for the other classes also?
Yes.
So you can do one for squares also, right? Okay. So let's say squares versus rest. Squares versus rest. So you have squares, and then X's will be represented like this. So do you think squares class will be given a good prediction, by the way? So either it will be here or it will be the other way around, right? 2 samples will be misclassified anyways. Yes or no?
Yes.
2 samples will be misclassified anyways. So, I mean, whatever linear line that I can get, I'll get it from this model. Okay. Let's assume this is the line. And there would be one more model, which would be for this circles versus rest. It should be like this. Okay. And let's call it circles versus rest. Okay. So the idea is very, very simple. So you have 3 models in this case as well. But do you think I need any other model, by the way?
No.
3 models here also, right? Okay. So first model is, say, class 1 versus rest. Let's just keep it like this. This is 2 versus rest. Let's say 3 versus rest. Okay. Please remember, I'm going to give the label 1 to this class always, the actual class. Okay. Rest will be given the label as 0. Okay. So I have a sample which is, say, age is something, height is something. Let's say 30 and 24. Okay. I want to predict. So what do? Is I pass this sample to M1. M1 will predict a real number, theta naught plus theta 1 x1 plus theta 2 x2. You take the sigmoid of it, you get probability score. Let's say the probability score comes down to be 0.65. So can I say that I'm 65% confident in favor of class 1?
Yes.
Yes or no? Okay. Let's say I'm not going to worry about the other class. Okay. Forget the other class for now, because that has multiple classes. Let's say this model 2 gives me a number 0.8. So I'm 80% confident that it is class 2. Does that make sense?
Yes.
Yeah.
And let's say this is 0.73. So 73% confident that this is class 3. So you have 3 predictions now, what you should predict. You have 3 predictions now, what you should predict.
Maximum.
Maximum of this. The class with the maximum probability. So here also you predict the class with the maximum probability, which is class 2. Okay. Does this make sense?
Yes.
All right. Now let's see the contrast between the 2 strategies. So first of all, one thing is, if you have K classes, how many models will you train here?
Okay.
Is it clear to everyone why? See, for every class, you're going to do 1 versus others, 2 versus others, 3 versus others, 4 versus others. If you have k classes, you will do k versus rest. You will go up to k versus rest. So exactly k modules. Which is more expensive? This or that?
1 versus 1.
1 versus 1 is more expensive. Okay. Another thing that I want you to look at is, look at this 1 versus 1. Okay. In every model that I am making, do you realize that I'm missing some of the samples? I'm basically discarding some samples.
Yes.
Okay. So there is some information loss which is happening for every model because I'm not considering all the samples. Yes or no?
Yes.
Okay. All right. Keep that in mind. So is the same loss happening in 1 versus rest? The question is, are you using all the samples in 1 versus rest for every model? Are we missing any samples in any of the models? Look at this. Okay. Here, how many samples are being used to train, say, let's say this model? So on the picture also it should be clear, right? I'm not missing anything.
Yes.
Okay. All the 6 samples are used, right? If you look at any picture which I have drawn here, how many samples do I make? 4. Okay. All right. Okay. But there is a big problem. When you want to train an ideal model, what should be the ratio of zeros and ones?
Almost equal.
Almost equal. Does that happen here?
No.
No.
But does that happen in 1 versus 1? Assume that originally every class had the same number of samples,
Yes.
which is by the case here. Okay. So I'm going to write the bottlenecks. See, if you look at 1 versus 1, this suffers from information loss. Okay. More compute intensive. Because you're training K-choose-2 models. Okay. But the good thing is, what is the pro of this approach? That the 0:1 ratio, can I say the classes remain, I mean, the original class ratio remains the same, okay?
Yes.
The data sets are balanced, okay? Let me call it relatively balanced because it will depend on the original number of samples, right? Yes or no?
Yes.
It depends on the actual number of samples in the class. The examples that I took where every class has 2 samples. Okay. All right. In 1 versus rest, the cons are, so this imbalance is high. If I assume every class has equal number of samples, what would be the ratio of zeros and ones? Assume every class has equal number of samples. Has the same number of samples, okay?
When we say it is model wise ratio, like
The model ratio would be the same, by the way, for every model.
so it will be one class versus rest class, like 1.
K minus 1:1, right?
Yes.
Okay. This would be the ratio, which is highly imbalanced, right? And a highly imbalanced data set typically will give you the answer as a 0. All right. And the pro is that no information loss and less compute intensive. Okay. Now there is one more strategy which is a hybrid of the two. Even these two are not in your syllabus. Shall I cover that also? Tell me this. Even these two strategies are not in your syllabus. Okay. Do you want me to cover the third strategy also,
Yes.
which is like a hybrid of these two?
Yes.
Okay. Now that is a little intricate. So please try to follow that. Okay.
One question.
Yes.
Question. Like in any of the strategies for any class, if the probability score for 2 classes comes out to be equal,
then you have to take a call.
Okay. And will masking be an issue in the one
One
versus
versus rest. Yes. You cannot avoid it. Yeah. You cannot avoid. Good question. Okay. So I'm going to show you a hybrid strategy of these two. So that strategy will train lesser models, will have no information loss, and it will be balanced. Okay. But this is actually more compute intensive than all of them. Okay. You will soon understand the reason why. Okay. But typically this can give you better results than all of them, but it is more compute intensive. Yeah. Let's see. Overall, it is more compute intensive, but the number of models that you train will be lesser. Okay. I hope, as of now, I don't think you probably get this idea why it is more compute intensive if it is training less models. Because you have to find how many models will do the best. Okay. So let's see. Okay. Okay. I have one question for everyone. Okay. Rather, let me give you a small analogy. Let's say I have 6 classes from class 1 to class 6. I have a simple question. If you were using 1 versus 1, how many models will you train?
6 choose 2.
What is that number? 15. Is that clear? You can do it in your head. 6 into 5 divided by 2. 6 choose 2 is 6 into 5 divided by 2. That will come down to be 15. If you are doing 1 versus rest, how many models will you train?
6.
6. So I'm going to show you a strategy where you will fix the number of models. So give me a number between 6 to 15. Or shall I choose a number myself?
Choose yourself.
Okay, so let's say I'm going to choose this number. Let's call it, say, okay, I'll start from, I'm starting the indexing from 1, okay? Don't get confused. So I'm going to choose this number, let's say 9. Let me choose 8, okay? With even, it is easier to explain. With odd, you will ask questions, what should you do? And the answer is straightforward. All right, but let's discuss it with this even number first. Okay, so I've chosen 8. So this is like the number of models that you will train. Is that part clear? These are the number of models. So 8 number of models you will train. Is this part clear?
Yes.
Okay. Now, for this strategy, what you have to do is this. For each class, just make a random binary vector of length 8. So don't you think this is a random binary vector? Yes or no?
Yes.
Okay, so I can make this random binary vector any way I want. Okay, so I'm just making it like typically. Okay, even though you can see there is a fixed pattern that I'm using, but assume that they are filled randomly. Okay, assume that they are filled randomly. Okay. So do you think that you can fill all the rest also?
Yeah.
Just numbers, right? Okay. Now see this. So in the data set, so you have some features. This is your output. So I want you to focus on this. If your output is 1, you are going to replace it with these 8 outputs, which I called it as, this time I'm going to call it as y1, y2, up to say y8. So can you replace this vector of 1 with this vector that you wrote here? You can, right?
Yeah.
So just say 0, 0, 0, 0, 1, 1, 1, 1. Okay, does that make sense? If you see a class 6, or maybe say class 4, I made a vector for this. What was the vector? So for class 4, it is 1, 1, 0, 0. So can you do it for every class like this? You can, right? Yes or no?
Yes.
Okay. Now I want you to visualize what is happening. So I'm going to use this output vector 1 to train my first model. Okay. So my first model M1 is nothing but use all the features and predict the output Y1. So don't you think I can actually use a logistic regression or SVM for this?
Yes.
It is binary by nature, right? Do you see that the outcomes will be here nothing but zeros and ones only, right? Yes or no?
Yes.
Okay. So I've converted my data set into binary. See, each of the meta strategies that we are using, do you see that it actually transforms your outputs into binary? Yes or no? The output vector is the vector of the form of zeros and ones, right?
Yes.
Yeah.
Okay. So how many models will I train here?
8.
8. Okay. So the 8th model will be use all the features and predict the output Y8. Okay. And let's try to discuss some other things. So you have these 8 models. Okay. I give you a sample which is d-dimensional. So this is the sample that I'm giving you. And you have to predict. So typically what do? We give this sample to M1. It will have how many total parameters? D plus 1, right? D coefficients, 1 intercept. So you'll get a real number output for this.
Yes.
If you do the sigmoid of this, okay, if you do the sigmoid of this, you'll get a probability score. If I get the probability score as 0.65, what would you finally predict? 1 or 0?
1.
1. Okay, keep that in mind. Okay, the value that I get, okay, is say 1. The value that I get is 1. Okay, similarly, if I get 0.3 here, what would you predict?
0.
0. Okay, so do you think I can get the 8 outputs just by doing this for each model?
Yes.
Okay. All right. Okay. So this is called as a predicted vector. Now, ultimately, you have to predict whether it is class 1, 2, 3, 4, 5, 6. Like out of the 6 classes, which class it is. So do you think that I can compare this predicted vector with the actual vectors that I started with? The class vectors? Yes or no? These 6 class vectors that I did?
Yes.
Okay. So I'm going to say, give you the predicted vector and you tell me, okay, let's say the predicted vector is this. Which class is the most similar to? Compare it with top 4 classes, just for doing this quickly.
Class 2.
Class 2. And how much is the difference? In how many bits do they differ?
Only 1.
1 bit, right? This is the bit in which they differ.
Yes.
Okay. So can I say that I can simply count in how many bits do they differ? And I will know whichever vector is the most similar. Does that make sense?
Yeah.
Okay. All right. So which operation, if you have done a course on, say, flip-flops or digital logic, or say simple gates and you have studied different types of gates, right? In electrical circuits.
Yes.
Yeah.
Okay, so which operation gives me this? So if I feed in 2 inputs, if they are the same, the output should be 0.
Feeding same output.
If I feed in 2 inputs, if the both inputs are the same, the output is a 0. Which gate it is?
NAND.
No.
The output's same, right?
NAND will give you 1 if both are the same. NAND, if both are zeros, NAND will give you 1. Think. By the way, are you able to follow the discussion that we are having? If some of you are unable to follow, please ask. Okay. Which operation it is? If both inputs are the same, the actual output is a 0. The output
Oh,
given by the
0.
gate is a 0.
Okay.
Okay, which gates have you studied?
Nor.
Buddy?
And
Sorry.
And or nor and
Yeah, XOR.
XOR is the
Yes.
answer to this.
XOR. Okay.
0,
So what does XOR give you?
0, 0 will be 0, and then it's XOR
1 will be
1.
1 is 0. XOR means that sorry.
1 1 is 0. Correct.
So when both inputs are the same, the output is a 0.
0. Yes.
Okay. So do you think that I can do the XOR of the two vectors? Look at this. I can do the XOR of compared and the predicted vector and any of the class vectors, and I can simply count how many ones do I get. That will tell me how many bits are different. Huh? Yes or no?
Yes.
Okay. And that will tell you. See, if you want to count number of zeros, that will also work. Okay. So more number of zeros that you get in the answer, right? Or what percentage of zeros are matching? Okay. How many non-zeros are, how many non-ones are there? That you can also count. Okay. That will still work. Okay. All right. Okay. Some basic questions about this. Now, the first question that I have is this. Am I suffering from any information loss? Am I discarding any sample? When I'm training a model using, say, Y1, do you think any sample gets ignored?
No.
No, right? All samples are being used, so there is no information loss. You can see the table. Okay, all samples are being used. Okay. Let's talk about the ratios of zeros and ones. Okay. Now, do you realize that I'm going to fill these numbers randomly, right? Yes or no? Okay.
Yes.
So, can I say that in output Y1, okay, wherever there would be class 1, what should be the bit 1?
0.
Wherever 0, right? Wherever you will see class 1, okay, wherever you will see class 1, the first bit would be a 0, right? Yes or no? Because I'm going to replace it with this vector. Okay. Similarly, wherever there is class 2, what do you think the first bit would be?
1.
1. Okay. All right. Now, listen to this very, very carefully. Okay. Assume equal number of samples for each class. Assume the same number of samples for every class. This is just to illustrate something. Okay. Okay. So one of the questions that I have is, if you have 6 classes, okay, if you have 6 classes, if I fill this 6 places randomly, what do you think is the chance that I get? Okay, let's talk about the first place. What do you think is the chance that I get a 0 here? I have 2 possibilities, right? 0 and 1. So with what probability I'll get a 0?
50%.
50%, right? Okay. With what probability I'll get a 0 in the next place?
0.5.
Okay, so can you tell me the expected number of zeros in these 6 places?
In 6 places, right?
What is the expected number of it? So if you repeat this experiment for 6 places, how many zeros will you get in general? Assume that it was infinite. How many zeros will you get if you're filling infinite places?
Infinite number of zeros.
No, by 2.
Infinite number of zeros.
What is expectation? Expectation is when you repeat something many a times, okay, the output that you get, okay, should reflect the average. So see, you have 50% chance that you'll get a 0 in one of the places, right? So if you repeat it for infinite boxes, in how many boxes will you see a 0? Infinite by 2, right? 1 also has the same probability. Yes or no?
Yeah.
Does that make sense? Okay. So in general, if I ask you, how many places you will see a zero when you are filling 6 boxes?
3.
3, right? Okay.
Yep.
Because if you fill it randomly, can I expect that? Okay. What do you think is the most likelihood that you will, okay, which is more likely to happen? Do you think you get 5 zeros and 1 1, or 3 zeros and 3 ones? Which is more likely to happen?
3 zeros and 3 ones.
I'm not talking about which place it is, but do you agree with me that 3 zeros and 3 ones are more likely to happen?
Yeah.
Okay. And there are more combinations that you can think about it. Okay. All right. So now, okay. A simple question is this. If I say that every class has equal number of samples, the same number of samples, let's assume that zeros and ones were equal in these vector representations. How many zeros and ones will you see here? Think about this. So let's say that, okay, let's say that this is what I got. Okay, let's say this is what I got. Assume that every class has 60 samples or 50 samples. Okay, assume every class has 50 samples. So how many zeros will you see in the table? In this table in Y1?
This is also going in a probability of 50-50 or
No, forget about probability. I'm telling you, okay, this is the vector.
okay.
So wherever you see a class 1, what would be the first bit?
0.
0.
Wherever you see class 2. So for 50 samples of class 1, what will be the first bit?
0.
Okay. For 50 samples of class 2, what would be the first bit?
1.
1.
Okay. So if I say that every class has 50 samples, how many zeros you will see in Y1?
150.
150. Spot on. Okay. So how many total samples are there? If there are 6 classes?
300.
300. Out of 300, you'll see 150 ones, 150 zeros, right? Does that make sense? Yes or no?
Yes.
Do you realize that they are equal, balanced?
Yes.
So it doesn't suffer from imbalance problem also. Yes or no? It doesn't suffer from imbalance problem also. Okay. Now, there can be an imbalance problem. I'm not denying that. When would be there an imbalance problem? Then you get a large number of zeros, right? Like this. For bit 2, if you see, there are 5 zeros and 1 1.
Yes.
Okay. There can be an imbalance in that case. I'm not denying that. Okay. But even if you fill this randomly, if you think about it, what is the chance that this will happen? It will be very, very rare, right? Even if you have 2 ones, okay, this still has more probability than happening, okay, than the other one. I'm not saying that. See, the question is, I can make the optimal matrix also. Yes or no? Where I get 150 zeros and 150 ones. Does that make sense or not? I can make it, right? It will just take me more time. And I have to make it more intelligently. That's it. But even if you fill it randomly, don't you think it is more likely to happen that I get equal number of zeros and ones in every column?
Yes.
Yes.
Even in each row, if you think, I will get equal number of zeros and equal number of ones. Yes or no? Okay. All right. Keep that in mind. Okay. So typically we fill this randomly. Even the implementation does it randomly. Okay. Now, one thing that you need to remember is this. See, there might be a chance, let's say everything comes down to be a 1 or everything comes down to be a 0. Do you think we should train a model for it, first of all?
For everything comes 0 and 1.
For everything, if let's say everything comes a 1, what would be, so let's assume bit 7, if you see, everything is a 1, right?
Yes.
Okay. So for Y7, what do you think every output would be?
1.
1. There will be no zeros.
Yes. 1.
Okay. So do you think, is there a need to make a model for this? Whatever sample that you will pass, what it will predict?
1.
1. So what it is? Constant predictor. Okay. So you might see constant predictors. Okay. In when you train this model, when I show you the implementation, don't get confused there. Okay. So you might see something like a constant predictor. Okay. So don't get confused.
Okay.
Okay. Because this can happen, right? This is a random way of doing it. Yes.
Okay. So if that was happening, we have to deal with it, right?
You don't have to deal with it. It's like, because bit 7 will not contribute, right? Because if all the bits are ones, what do you think the output will be? Output will also be a 1, right?
1. Yeah.
Essentially, what you are saying is this bit can be ignored.
Okay.
Okay. It doesn't pay any heed in the contribution. Okay. Because output will never be zeros, right? Why would it be zeros? You don't need to train a model, right? Because the model will always predict a 1 no matter what. There are no zeros at all. Okay. So it is as good as saying it's a worthless column. Okay. All right. In this case, it's a worthless column. Okay. But you might see that in the implementation, so don't get confused. Okay. Now, ideally, if I ask you this, think about this very, very carefully. See, I'm giving you some intricate details right now. If you think about this, let's say I'm looking at the vectors of class 1 and class 2. Do you think if I take the XOR distance, if I do the XOR of each of the bits and I count the number of ones, which will tell me their dissimilarity by how many bits they differ? My question is this: should they be close by or should they be far apart? These individual class-wise vectors. What do you think? These individual class-wise vectors, should they be close by or should they be far apart?
The number of.
See, what we are saying is, let's say I do the XOR comparison between class I vector and class J. Any two classes. Okay. My question is, should the distance be high or low? Should the number of bits, which are ones,
Low.
so if they are low, can I say that the vectors are the same?
Yes.
If the vectors are the same, how would you differentiate
Use of
two
it.
classes?
Yes.
So that will be high, right? See, I think that the distance is low. Can I say that in that case, the least distance is 0, right? Then the
Yeah.
two vectors are exactly the same. So if two vectors are exactly the same, then how would you differentiate between class 1 and class 2?
Yes.
So they have to be far apart, right? Think about
Yeah,
this.
I missed it.
Yes. Yes.
So your goal is to distinguish between the classes, right? So they should be far apart. Does that make sense?
Yeah, yeah.
Okay. So I'm just giving you the counter argument for this.
Got it.
So each of the vectors should be far apart. Do you realize that?
True.
Got it. So I'm going to give you a conclusion, and this is like an understanding. Okay. Okay. I'm going to give you an understanding that even if you fill this data randomly, these class-wise vectors randomly, this will happen. Okay. Okay. So currently, how many bits are there?
8 bits.
Okay. What is the chance that bit 1 of class 1 and bit 1 of class 2 will be different? There is a probability that if you fill it randomly, the bit 1 of class 1 and bit 1 of class 2 is different. Okay. How many combinations can you make? Think. See, here
Common.
is to fill.
Four.
For out of 4, when are 2 different?
Two.
So you're filling 2 places, okay, with zeros and ones. Okay.
Two out of
Try to
four.
come up with all possible combinations. In how many combinations are they different?
Two.
2, right? And how many total combinations are there? 4. So what is the chance that they are different?
2%.
50%, right? Okay. So can I say that 50% probability that they will be different?
Yes.
Okay. You have 8 combinations. Out of the 8 combinations, okay, can I say that 50% will be the same and 50% will be different?
Yes.
Yes.
Okay. Very high chance, right? So out of the 8, how many will be different?
Mm.
General sense, right? Okay. So even if I fill it randomly, do you think that they will differ by 4 places?
Yes.
And this will hold for any possible pair, right? Yes or no?
Yes.
Okay. If you realize that this is going to happen, okay. So even if you do it randomly, it works. Okay. That's what I'm telling you. Okay. So this is actually called as horizontal separability. Okay. This is called as horizontal separability. The idea is that the class-wise vectors should be far apart. Okay. So ideally, this class-wise vector should be greater than or equal to number of modules by 2. Does that make sense?
Yes.
Number of modules is actually the number of bits that I took. Okay. So this much has to be the separation for an ideal model. Okay, for an optimal vector that you are constructing. But even with random, it comes down to be 4. Okay. Okay. Now I have a question here. Let's say is there a possibility that 2 bits can exactly be the same? Yes or no? You're filling it randomly, but there is a chance that they might come out to be the same.
Yes.
Yes.
So if they are exactly the same, do you think the modules differ?
Mm.
Let's say bit 1 and bit 2 are exactly the same. Okay. Do you think that y1 and y2 will differ?
No.
No, right? If y1, y2 don't differ, then models are the same, right?
Yes.
Okay. So so do I get any fruitful value? If
No.
no, right? Okay. This is called as vertical separability. Okay. Now think so is it likely to happen? Think about this. In by how many places these column vectors should differ or will differ in general? There are 6 values to fill.
Again, 50%.
50%. What's the number? 3, right? Yes or no? Okay. So by number of classes divided by 2. Does that make sense? Okay. So this is a concept which you should know. They might ask you this. Okay. This is for your class wise. Okay. Sorry, this is class wise. This is model wise. All right. So these things should hold, and they hold really well when you are doing random matrix generation. Okay. So this is some concept that you should know. They might ask, they might not. And this strategy is called as error correcting output codes. This strategy comes from information theory. I'm not going there. I will have to explain information theory, how bits are transmitted. Okay, and how does it relate to this? Okay, this idea comes from there. You can just note this. In the implementation, this is called as output code matrix or output code. It's called as output code classifier. In the implementation, it is called as this. Now, please note this. What should be a hyperparameter for this? Hyperparameters are those entities which you manually tune. You specified something in the beginning manually. What was that? Okay, let's take a step back. When you started 1 versus 1, how many models did you train if you had k classes?
K choose 2.
In 1 versus rest?
K.
Here, what did you do? You set something, right?
Yes, number of models.
Okay, number of models. Okay. Please note that there is this hyperparameter called as number of models, but this is not the number of models. They call it code size. Okay, they call it code size. So code size is nothing but equivalent to, please listen to this very carefully. So code size is nothing but equivalent to, let's say you specify code size as 2. Okay, so code size is, okay, this code size is nothing but equivalent to code size into number of classes is equal to the number of models. So for the given example, if I say code size is 2, what do you think the number of models will be? How many classes do I have right now?
6.
6. Okay. So if I make it 2, how many models will I train?
12.
12. Okay. So to make it 8, what should be this number? You can compute it, right? This should be 8 by 6, right?
Yes.
Okay. So put 8 by 6 here. Okay. Does that make sense? Okay. So the hyperparameter that you will put right is called as code size, not the number of models. Okay. In the implementation, they call it like that. Okay. They will not call it number of models. They'll call it as code size. Okay. So we will see the implementation today. Yes. Any questions? Is this clear, right? Okay. Now the question is, if this is the hyperparameter, think about this. Is it guaranteed that if I take 8 models, I'll get the best results?
No.
So I have to search for all of them, right? In what range I should search for 6 classes? Ideally, between what range? Between 6 and 15.
6 and 15.
Between 6. You can actually go higher than 15 also if you want. Okay, nobody stops you. You can actually go lower than 6 also if you want. Nobody stops you. But in my experience, you get the best results between the range of, say, when code size is 1, and between 1 and 2. Okay? Between 1 and 2, you get the best results. Okay. Typically, between 1 and 2, you get the best results. In my like for most of the experiments, maximum you can go up to 2.5. You don't have to go that really far. You don't have to go really far. Okay, which is actually much smaller than K choose 2. So think about 10 classes. If the highest code size is 2.5, how many models will I train?
25.
25. And if I were using 1 versus 1, how many models will I train? 10 choose 2. That number is 45. Okay. So you can really save a lot. Okay, you can really save a lot. Okay. So these are the strategies that I'm going to show you today. Okay, let's implement them. Okay. Any
And
questions?
Sanatan,
Yes.
actually, I've joined late, but on last session we had that penalty thing
That
is
I'll
not
talk
worked.
about. Yeah. And maybe
Okay.
at the end we'll discuss it. I found the answer to this.
Okay.
Yeah.
And one more thing, like in this, we are reducing the number of models as compared to 1 versus 1.
Correct. But don't
Computation reduce.
it will take more time, no? So you have to search, right?
Yeah, so that's what like this was my question, but the time taken will be more because searching and then XOR is also there.
No. That is not that much time consuming. The time consuming part is training the models.
Okay.
Okay. Because prediction would be done for those also, right? So let's say prediction time is just twice. Okay. But it depends on the number of test examples, right?
Yes.
Test examples that you have.
Yes.
So it's not going to be that high. Okay. Training models is going to be the obviously, yes, you're training less number of models, but you have to find, right, for 8, 9, 10, 11, 12, 13, 14, which is the best number. Okay. So that can take time. Okay. Any other questions? Yes, people. Any other questions about anything? The SVM part I'll discuss at the end.
Okay.
Otherwise, there will be a break in between, right? Push this. So I'm going to do it relatively quickly today. So if you have any questions, please ask. Okay. You can stop me any number of times in between. Okay. So your batch is DSM-04.
Yes.
Okay. And let's say, okay, this is, let me just simply call it as meta strategies. By the way, there are so many meta strategies. I mean, if you can explore on your in your free time, you can check them out as well. Just search for meta strategies, you will see many. Okay. But the ones that I've told you, they are the most popular ones. So, okay, let me import pandas and NumPy, and let's import a multi-class data set. And okay. So let's import a multi-class data set. Okay. Which data set do you want me to take? Iris has 3 classes. Digits has 10. This wine has 3 classes. This breast cancer has 2. So these are the classification data sets. What do you want me to use?
Go digits, like it has a
It's okay.
class.
It has 10 classes. Okay. All right. So let's load this data set. So the idea is we are given 64, I think maybe 28. Let me see. Okay, I think it's 28, 28 each image, and we have to predict what digit is there in the given image. So how many digits are possible?
9.
10. 0 is also a digit, right?
Yeah, 0 to 9.
So total 10 digits. So that's why there are 10 categories. Okay. So let me print the description of this data for you. So it's 8 cross 8, sorry. So 64 pixels only. So every image is 8 cross 8. So basically 64 features. Number of images are 1797. So the data set size is 1797 times 64. Okay. And the output is like one of the 10 classes. So if it is 0, which means 0 digit, 1 means 1 digit, and so on. Okay. All right, let's load this. So these are the features. These are your outputs. Okay. So just to show you what is the ratio in Y. Okay. So this is the ratio. It looks almost balanced, right? Yes or no?
Yes.
So there are 10 classes, as you can see. These are the outputs, by the way. You cannot see, I mean, because 1797 outputs are there. A total of 1797 samples. Okay. And the number of features are 64. Okay. 64 features. Okay. So I'm going to split this data. Okay. Let's split it. Before that, I'm going to show you the minimum and maximum values. Okay. So let's see the minimum values across all the features. Okay. Do you see that all minimum values are zeros?
Yes.
These are grayscale images. Okay. Or maybe binary images. I don't remember. Let's see. What is the maximum value? I believe it will be 255. That's 16. So it's integer images. 2 to the power 4. Okay. So you can see that minimum is even the same. Maximum is different, right? Okay. So you can scale if you want. Okay. So you can do the scaling if you want. I'm not going to do that. Okay. I'm just letting you know beforehand that you should scale, because you can see the ranges are different, right? For the maximum. Some cases it is a 1, some cases it is a 2. Okay. So you should scale. Okay. I'm not going to waste that much time. Okay. This is just done to ensure that I want to show you something. Okay. That's the main part of it. So let's go to model selection, split our data into 2 parts. Though it will not create much difference at all in your results also for this data set. So we have split the data into train and test features respectively, and then the train and the test outputs. Okay, so these are the number of samples in your train. Okay, and the remaining in your test. Okay, so what I'm going to do is I'm going to train a simple logistic regression model for you, and we'll show you something first. Okay, so logistic regression model is present here in logistic regression. Okay.
Should we stratify a split?
You can do that. Say, okay, so stratified as well. Okay. So I'm fitting the model onto your data. Okay. Now please note that there is this argument called as multi-class. Okay. By default, this is mentioned to be as auto. Okay. So the auto value is 1 versus rest. Okay. The default value is 1 versus rest. Yeah, the default value is sorry. Let me see. Is it? I believe it's multi underscore class. Or maybe say 1 second. I misspelled it. 1 second. It's multi underscore class, I believe. Yeah. Okay. So it is telling you that okay, iterations are required more. Okay. So I can actually increase the iterations. Yeah. Okay. So this is 1 versus rest. So if I ask you how many intercepts will I get? Think about it. How many models do you train? There are 10 classes.
10 classes, 10.
Okay,
10.
so 10 classes, so 10 intercepts will be there. Count it. Does that make sense? So for each model, there is an intercept. Is that part clear? And how many coefficients will be there overall?
640.
640. 10 into 64. Okay. I'll show you the shape. Okay. Does that make sense?
Yes.
Okay, great. These are coefficients. Let me just print the shape of this. Okay. Okay. So, and now if you want to make a prediction, right, you can simply say model.predict and pass the test set. This makes a prediction. If you want to do predict proba, you can do that. And for every sample, it is giving you the 10 probability scores. Is this part clear?
Yes.
For every sample, it is giving you 10 probability scores. Yeah. Anything else that you want me to show? Anything else that you want me to show? I mean, you can apply the accuracy, precision, recall, and all of that on your own, right?
The probability, the predict proba that it is showing the result. How will I know in that particular, like for which class that is the probability? Like which
the class
level is taking as class 1?
Vector, okay, I'll print the first vector. Look at this. These are the 10 probabilities. Okay, just by looking at it, can you tell me which is the highest?
The second one?
Second one, right? This looks like the highest. Now, if you want to know, so which class it is?
It would be class 1.
0, 1, 2. So class 1 is the highest, right? Do you see the output is 1?
Okay.
Okay, makes sense. So if you want to see, okay, like in NumPy, there is this, function called as argmin or argmax, okay, that you can use to get the index of the maximum value. Okay, so if you want to get the index of the maximum value, so you can simply say argmax and it will give you the index of the maximum value. Okay, that's why you see the prediction is a 1.
Okay.
Does that make sense? Okay, I'll do it like this. Okay, so that way you'll see for all the samples. Sorry, it actually gives you for across all of them. No, sorry. This is giving you 1 second. Yeah, now you can compare.
Okay.
Just shorten it for you. Okay. Do you see that the results are the same, by the way?
Yes.
Okay. All right. So you are essentially finding the maximum of the 10 values and printing that index. So is this clear?
Yes.
Okay, I'll just comment this out if you want to know this. Or shall I keep this? Tell me, please.
Yes.
Okay. Okay. All right. Okay. So this is about your logistics. So logistics supports 1 versus rest, but it does not support 1 versus 1. Okay. Please remember this. There is one more strategy. If you're interested, you can read about multinomial. So this logistic also supports multinomial. Okay. But the default strategy is 1 versus rest, which works really good. I'm going to show you then about SVM. What do you do? So in sklearn with SVMs, you can import SVC, and in SVC also there is this. So SVC supports both 1 versus rest and 1 versus 1. Okay, and this is also called as, I believe, multiclass. Okay, so it supports 1 versus 1 versus rest as well. Just a second. Okay, there's some problem is there. Oh, sorry, small SVM. Okay, what does it say? It's multi underscore class probably. Let me check. It's decision function shape. Okay, that's very weird. Okay. All right. So you can do 1 versus 1. Okay, and this will. So if you think about it, please note that if you want the I mean, the kernel, right? I mean, if you want to get the coefficients, the kernel has to be linear. The default kernel is RBF. Otherwise, it will not return you intercepts. And okay, so how many intercepts will be there? There are 10 classes.
10 choose to 25. No,
No, 10 choose 2 is 45.
45.
Okay. All right. I'll just print the shape for you. Okay, makes sense. And if you look at the coefficients, how many coefficients will be there? 10 into 64. Sorry, 45 into 64.
5 into 64. Yes.
45 into 64. Okay. Make sense? Okay, so you can still use model. If you want probability, put probability as true. Put probability as true. Okay. Does that make sense? And then you can use predict, proba. And this supports OVR as well. Okay, this supports OVR as well. Okay, here you can use OVR also, but logistic doesn't have. Okay, I'll just mention it. Logistic doesn't have. I'll just mention it. This one doesn't have OVU. Okay. So how do you implement with 1 versus 1? Okay, that is what I'm going to show you next. So you go to sklearn dot multiclass, and you have to import. So which one do you want to implement first? 1 versus rest, 1 versus 1, or error correcting output codes?
1 versus 1 first, then we'll go.
Let's go with 1 versus 1.
And could you please zoom in?
Yeah. Okay. Visible now?
Yeah.
Maybe I'll work it on. So what you do is you say call this as 1 versus 1. Okay. Instead of calling it as 1 versus 1, let me call it, say, 1 versus 1 classifier. Okay. Because OVO is an argument there. Okay. Okay. So see what this strategy will do. It will convert a data set into binary data sets. So you have to tell which model do you want to apply. So which model do you want to apply here? Which one? See, you can even apply multi-class classifiers here. So what this strategy is doing, 1 versus 1 classifier, this is going to give you a transform data set. You have to specify what model to use. So this is like a generic function, which will convert your, you can say, multi-class data sets to binary. So which one?
Now on this 1 versus 1 classifier, after this, I can apply a logistic model.
You can apply k-nearest neighbor support vector.
Now same as my normal binary data.
So what this will give you, they will give you binary data sets.
Yes.
These binary data sets, you will apply some classifier, right?
Yes.
So so see, think about this. A multi-class classifier can be applied on binary data sets also.
Yes.
Okay. So if you want to do that, you can do that as well.
Okay.
Okay. So this is like generic way of transforming, and then you specify. Okay. So I mean, ideally, it would make sense to use binary classifiers, right? But I'm saying you can use multi-class also on them. Okay. And multi-class can be used directly also on any data set, right?
Yes.
But these functions are there to transform your data sets into binary.
Okay.
So tell me for which, which model do you want me to apply after this converts it to binary data sets?
Logistic.
Okay, let's go with logistic. So your model is logistic regression. Okay. So I'm going to specify 1 versus 1 classifier. This is your model. Okay. And you have to, this is your model, and then you can fit this OVO underscore classifier onto your data set. So your data set is in X train and Y train. Okay. Sorry, there's a problem. I misspelled it.
Yeah, logistics. I think you missed.
Okay. It's called as 1 versus 1. Just a second. This V is probably small. Okay, let me just check. I'm misspelling it probably. Okay. I didn't run it. Sorry. Okay. So it's telling you limit. I mean, basically, it's saying iterations reached. So you can increase the number of iterations here. So this will not show you this pink warning now. If it shows again, increase the number of iterations. Okay. So if I ask you how many estimators are there, what would you say? There are 10 classes. In one, how many estimators would be there?
45.
So you can get all those 45 estimators. See this. So it's giving you all the 45 estimators. Okay. Sorry. Oh, it's a tuple, so I can count the length of this. Okay, makes sense? Yes. Is this clear? So you can get individual models also. So if you want to get individual models, so you can do it like this. Okay, I want the first model, I can go with the 0th argument. Okay, if you want the coefficients for these are the coefficients. How many coefficients will be there?
64.
64. Okay. Similarly, you can get, the intercept of this one. So that will be just one intercept. Okay. Does this make sense?
Yes.
Okay. So this is how you train. And now if you want to predict, right, you can use this one versus one classifier and make the prediction using the predict function. Using, pass the test set to it. It computes the predictions. Okay. Please note that one versus one does not support predict proba. You can reason why. See, one versus one will not support predict proba. Why? Any guesses? Okay, so you remember the example that I took for 3 classes?
Yes.
Okay, so how many models will give you the prediction in favor of, say, so let's say you're using 10 classes, okay? So how many models do you think will differentiate class 1 from others?
In whichever we have class 1, so 10.
9. 1 versus 2, 1 versus 3, 1 versus 4, it will go up to 1 versus 9, right?
Yes.
Well, because one will be starting with 2, right?
Yes.
And you can, you can start from 0 to 9. So how many models are there? 9 only, right?
Yes.
One will not be differentiated with itself, right?
Yes. Yes.
Okay. So your total number of predictions in favor of class 1 are how many?
So there will be 9 predictions.
Right? So how do I know which is which one?
Yes.
I don't know that, right? So predict proba does not make sense there. Okay. But then if you think about 1 versus 1, how many will be in favor of class 1? Only 1. When you say 1 versus rest has a lot of other things, right?
So that probability will be more.
No, you think about this. See, when I'm trying to use this predict proba method, I need to know the probability for a particular class, right?
Yes.
So if you're doing class 1 versus rest, you have one probability for class 1, right? Do you have any other model which is giving you in favor of class 1?
No.
No, right? So that is why you can use predict proba for that. So in 1 versus rest, you can use it, but not here. It will throw an error. Okay, let me just show you. It will say that predict proba is not supported. Okay. Okay, see this. Does that make sense?
Yes.
Okay. So maybe keep this in mind. This is an interview question which is asked. Yeah. Okay. So this is how you use this. I'm going to show you now 1 versus rest. So all of them are actually in the same library. This is sklearn multiclass. Let's call it as OVR versus. Okay. Okay. So now if I ask you how many modules will be there right now?
10.
10. So here we are in score C. Okay. All right, makes sense. And then you can use, you can, sorry, it's a tuple, my bad. So then you can use like any particular estimator by the index. So the first one will be class 0 versus rest. Second one will be class 1 versus rest. Okay. So this is your class 0 versus rest. Okay. And you can get the coefficients and the intercept the way you want. Okay. I'm going to show you that it supports both predict and predict proba. Okay. So this is the sorry, it's OVR underscore C. My bad. Okay. And it supports predict proba also. It will give you the 10 probability scores for each sample. Does that make sense? Okay. So this is your 1 versus 1. Okay, you can make comparisons based on some metric, and you will see that 1 versus 1 is typically it performs better than 1 versus the rest. Okay, but it is more compute intensive. Okay, maybe I'll show you the last one, which is your output code classifier. So let's call it, say, OCC. Sorry, I didn't mention the argument name. By default, port size is, I think, probably 1.5. The default code argument is 1.5. Okay. So with 1.5, how many models I am training?
15.
15. Okay, just a second. It's called as, I believe, 1 second. Let me see. It's code size. I don't think there is any space. Okay, let me just check. Code underscore size. Yeah, the default is 1.5. Was I misspelling anything? I called it as code size only. Oh, sorry, I was specifying it here. See, I'm done. My bad. Here. Okay, so you'll see that there will be 15 classifiers. Just to show you the length of this. Okay, makes sense. And now you can get C coefficients and anything that you want. If you want, I mean, to use the predict and predict proba, I think it supports predict proba also, because once you know how many misclassifications are happening per class, because you will know the dissimilarity for every class, right? From that, you can estimate what is the probability. I believe it supports predict proba also. Okay, let's see. I think it should. Anyways, let's check. No, it doesn't. It doesn't support it. I thought it would have, no, but it doesn't. You can actually make a predict proba out of this though, because once you know, once you compare the predicted vector with the actual class vector, right? From the misclassifications, you can estimate like what is the probability. Like if a class is having, say, no misclassifications, no, but then it will become a 0. That is a problem. Understood. Okay. All right. So this predict proba is not there here as well. Yeah, so this is what it is. Any questions about OCC or any other thing? Do you want me to show how do you tune it? You just have to choose a metric and run probably a grid search on it. Okay, maybe I'll do it directly. So, see, these are the same steps that you have seen. So, from model selection, I'm going to run randomized search. Okay, I don't want to, because this also will take time. Okay. And stratified k-fold. Let's do it for the 5 folds. So specify your parameters. So in my case, the parameter is just port size. Okay. And I'm going to search it in the range of say 1 to 2.5, or maybe say 1 to 3. So checking for 20 values and looking. Okay. Do you want me to tune anything else? Yes, do you want me to tune anything else? You can tune actually logistic regression parameters also if you want. Is this fine? I mean, you can first get the best performing logistic regression model, and then you can use it. Okay, just a second. Maybe I'll make a small pipeline which will do your normalization or scaling as well. Let's do standard scalar. Sorry. Second.
Can
Let's,
I even parameterize like which classifier is good for my prediction?
how?
Like I run the code with, will my outputs and the performance of the model be different with 1 versus 1 and 1 versus rest? It will be different.
Yes.
So how will I see which is better in whichever the accuracy score
Yeah,
is better?
whichever the evaluation metric is better, right?
Yes. So that thing, rather than like in the pipeline, you'll be mentioning the classifier also, and then so that classifier, can I parameterize?
The pipeline, you will not do this.
Okay.
See, pipeline is a sequence of steps, right? You cannot say one step is comprising of multiple steps.
Yes. Okay. So first you'll do the class. Okay, got it.
So you have to run it individually for 1 versus rest, output mode classifier, and other things. Okay. So the first step is your standard scalar. The second step is your model. Let's call it OCC, output mode classifier. Underscores. Yeah. Let's
After
call
OCC, you have given a comma or
here.
about like my steps.
Yes. Given in comma.
OCC after
Standard
that.
scalar tuple, the standard
Yeah.
scalar tuple.
This is the standard scalar tuple. Oh,
Yes.
sorry.
Yeah, after that, like OCC.
Thank you. There was a slot here. It should be a comma. Yeah. All right. Let's pass your pipeline here. The parameters distributions, which is just params. Let's call it hyperparams to make it. Okay. And cross validation technique, which is stratified k-fold, and the scoring metric. Which scoring metric do you want to use?
Accuracy.
Let's go with accuracy. This problem.
Where have I fitted the model? Like in this? Okay, in the output. Okay.
In the output code classifier, the model is going here. Okay. Have I misspelled anything? Yes, R is missing. Let me use it on the entire hit. I mean, just change some bit of the code and you will know, okay, what is performing well. Is it OVR, OVO? Okay. Maybe I'll do that and then we'll see, okay, which one is going better. This typically will take time. That's the problem. I'm glad that I didn't run grid search CV. Otherwise, we would have to wait for a long time. Okay. I could have taken another data set like wine data set, which would have been easier. Okay. Anyways, let's do it for your one versus rest as well. Did you see this message? I just got a message. Okay, the results are there. This is the accuracy that you get. And this is the best port size. So it is 88.59 so and something. Okay. And I'm going to now run one versus rest. Okay.
That message was because of that n job things that you say?
No. So it's not because of n jobs. When the single processor is already is utilized to the fullest, right?
Yes.
That's why you get that message. Because your RAM is almost about to be consumed.
Okay.
So that affects the meeting quality and everything. So in some cases, my system might shut down. Okay. That is also possible. And just a second. So here there is no hyperparameters. Okay. Okay. There is no hyperparameters. What should I do? And I just need to run and then make simple comparisons, right? Okay. Or so I just need cross-val score for this. I still haven't made a fair comparison because here you have to specify a random state. Okay, please do that in the previous example also. Okay, these results might differ slightly. Okay, so make a random state here and rerun this. Okay, results will not differ by that much though. All right. Okay, just a second. Yeah, this looks all right. Okay, but I don't need this though. I don't need randomized search. I need cross-val score. So I have to pass the model, which is my pipeline. I have to pass the cross-validation, the data, which is an X and Y, the cross-validation technique, which is stratified k-fold, and the scoring metric, which is accuracy. So this will give me 10 values. Okay. See, this will give me 10 values. I'll get the values in an array. Let's say, so these will be ACC values. Okay. 10 values I will give. I'll print those as well. Okay, and I'm going to print the mean of these values. So one versus rest is actually doing quite good here. Okay, so maybe I should have taken assertion what range. See, I made a stupid blunder here. I kept this. I kept this. Okay, I fixed it. My bad. Okay. Just a second. Okay, I'll rerun this. Okay, just a moment. Okay. Okay, I'll rerun this. So this is the accuracy values. Okay, okay, this is fine. Let's do it for 1 versus 1. So this is for your 1 versus 1. Okay, anything else? No, looks all right. So you can see 1 versus 1 does slightly better. Okay, and now I'm going to run this again. Okay, just a second. Am I using max ITR as 10,000? Yeah. Random state as 1. Yeah, okay. Hopefully this will exceed these values, but you need to run a grid search in that case. Okay. Let me try. Okay, since I'm running randomized search, I might not get the as good as results. Okay, but let's see. Let's be hopeful that it will beat it. Okay. Otherwise, you can run it in your free time, run a grid search, and these values will definitely be better. Okay? 94.32, or it will be at least as good as this. Okay? It will certainly be better than this. Okay, if you run a grid search, and it will definitely reach this, but I'm not sure whether it will be beaten or not. It depends on the data set. Okay. So currently, since I'm running a randomized search, okay, it's not necessary that they will beat these two values. Okay. Maybe you can do it in your free time, and you will definitely see these values will be beaten. Any other questions? About logistic regression? Yes, people, any questions as such?
No.
Okay, then maybe once the results are there, I'll move to. Okay. Okay, so currently this is the code size, and you see, okay, we got some better results, but it is still not improving, I mean, than this. Okay, so you need to, I mean, do a grid search, and then you can run these experiments. Okay, so maybe what I'll do is I'll run a grid search. Okay, but then the system might fail. Okay, so what I'll do is I'll probably run a grid search here, and then shift to the other device. Hopefully, the meeting quality would stay the same. Otherwise, I'll switch on to the other device. Okay.
Okay.
So I just want to show you, okay, this can beat it for sure. One second, I'll just keep it for now. And
If you use Colab, you can avoid this issue, right?
to some extent, yes. But then I have to rerun every cell.
Okay.
Okay, let it run. Okay, let's discuss. Okay, let's discuss why SVMs are having that problem. Okay, and there is a generic argument for it, by the way. So they do follow that trend. Okay. So the idea in SVMs is the following. So if you look at, so I'm making a two-dimensional data set. Like this. Okay. So do you remember I spoke about this idea that if you want to find out that there are, let's say, two parallel lines like this, and the middle line would be the ideal separator.
Yes.
Okay. All right. Just keep this in mind. Okay. So what is happening is, let's say if you increase C, okay, we said that the model is kind of overfitting, right? The model overfits, and that is true. So increasing C will lead to model overfitting because C is directly C is the inverse of regularization, right? Yes or no? Okay. So let me give you an argument. Okay, why this happens? Okay, what do you think will happen when the model overfits? Will the performance on your data set will increase or decrease? Okay, think about this. Will the model performance on your data set, would it increase or decrease? What's your best guess?
Performance would increase.
Set on the training set.
On the training set, the performance will increase.
Right. So if the model performance is increasing, okay, what do you think? The distance between these parallel lines, would it be high or low?
High.
Think about this. If you make it higher, don't you think that the points inside will be incorrectly classified?
Okay.
Yes or no? Think about this.
Yes.
See, if I increase the margin, this is actually called as a margin, the distance between the parallel lines. So what would happen to the margin if you are increasing C? The margin would become smaller and smaller. They would become very, very close to each other because you would want to classify each point correctly, right? Think about this. Each line L1 and L2 is a good separator also, right?
Yes.
Okay, if you see in the image. So if you increase the margin, what would happen? L1 and L2 will not become good separators in themselves.
Yes.
So the margin has increased, but the classification performance would decrease then. So when you are increasing C, do you realize that this margin will decrease? Yes or no? When you are increasing C, do you realize that this margin decreases or not?
Yes.
Is this statement clear or not? So the margin will decrease if you increase C. Okay. So if you increase C, the margin decreases. Now, think of a very generic statement. Okay. If the margin decreases, what do you think? Will you be, I mean, when you are nearing, when the margin is very, very small, how many points do you think will actually lie on these lines L1 and L2? And they are all called as the support vectors, right?
Very less.
Very less, right? So that is why if you increase C, the number of support vectors decrease. Okay, we were actually countering it the other way around. We were thinking that, see, overfitting means, I mean, looking at more examples, right?
Yeah.
Okay, I mean, in general. So here we are still looking at more examples, but the definition of support vector says that the points which lie on the lines L1 and L2. So do you realize that now? Like if you increase the C, margin would get smaller and you would actually get to see lesser and lesser points. Support vectors are those points which lie on line L1 and L2. But you are doing a better job on all the points, right?
Yes.
Accuracy is improving. That is what overfitting means. You do very well on the train set. Okay. So the margin decreases and the support vectors also decrease. You can look at it from a pictorial perspective also. If I decrease C, what will happen? My model will become worse, right? On the train set. I'm talking about on the train set. The error would be more on the train set. So this will become bigger. Maybe the margin is now this. Okay. Do you realize that there are more support vectors now?
Yeah.
or no? I mean, so that is the relationship. We were actually countering it the other way around. We thought that like if we increase C, right? I mean, we were on the right track, but we argued the other way around. We forgot the definitions of support vector machine. I mean, what the definition of support vectors? They are the points which lie on the lines L1 and L2. Okay. And let me tell you one more thing. The implementation that we did, right? It was actually for something called as soft margin. Okay. And not, so there are two variants when we will discuss about the theory behind support vectors, right? So there are two variants of support vector machines. One is called as soft margin. The other one is called as hard margin. So what I'm telling you right now is hard margin. Soft margin actually goes a little one step further. And what it says is this. So if you decrease C, okay, if you decrease C, the margin becomes even bigger. Okay. So imagine if there were some triangles lying here. Okay, if some triangles were lying here on the incorrect side. So what soft margin says that these points are also contributing towards the line. These points are also contributing towards the line. So you get more support vectors. These points also contribute towards the line. So you get more support vectors. Okay. The points that are actually misclassified to increase the margin, they are also counted. Okay.
Yes.
Okay. In hard margin, you are saying that the points that lie on the line, they are the support vectors. In soft margin, if the points are actually on the incorrect side, they are also the ones which actually contribute, in addition to the ones that lie on the line. Okay.
If like in this case, the triangle will contribute on the L2 or
No, the triangle will. So it is like, see, a triangle is, if you think about it, if I ask you, which line is responsible for classifying triangles with respect to these x's? L1 or L2?
L1.
L1, right? So what we do is we incorporate a penalty with respect to L1 and count this distance, the points which are misclassified. Okay. So if I ask you this, if I make these distances, let's call these distances as D1, D2, D3. So if I make these distances shorter, what is happening to my margin? Is it increasing or decreasing?
The margin is decreasing.
If you decrease the distances, do you realize that you are kind of overfitting?
yeah.
Okay. So that's what soft margin says. So if you decrease the margin, do you realize that some of these triangles might also be correctly classified, but then some x's would get incorrectly classified?
Yes.
But so you would, so the idea here is this. So look at these lines, I mean, these points, these triangles. Okay. Now, don't you think I can look at it from x's with respect to this line L2? Think about this point. Okay. Think about this point as well. Okay. Are you able to see this x, which was previously, I mean, now it is on the incorrect side? Yes or no?
Yeah.
Yes.
Okay. So you will count this distance as well, which is D4. Okay. So if you increase C, what will happen is these distances would get shorter and shorter. Okay. These distances will get shorter and shorter, and the model will do better on the, you can say, the train set. But is it guaranteed to work better on the test set also? No, right?
No.
So you can try for different values of C, maybe try increasing the margin or decreasing the margin, and whichever model works best for you, use that. So these points, the 4 points that I've highlighted right now, let me put it in green circles. Okay. They also contribute. So in addition to the points that are lying on the line, these points are also counted in, okay, as your supports. Okay. That is why the number becomes even bigger. And when will this number become bigger? If you increase C or decrease C? Think about it.
When we decreased on that day, it was actually.
Forget about that. And now that you know the definition of it.
Okay.
Okay. So if you, so first of all, if you increase C, what will happen to these distances? Will it become smaller or longer?
Increasing C.
Think about it. These distances will become, okay. See, idea remains the same. If you increase C, margin will grow smaller. So if margin is growing smaller, will the distances increase or decrease? L1 will become closer to L2, right?
Distance will decrease on that time.
So the idea is when you are increasing C, the distances will also decrease. Okay, so maybe some of the points are not contributing now. Maybe this X that I'm highlighting, maybe it gets on the correct side, right? So you have reduced one of the distances, right? This distance is not counted. This D4 might be. So if okay, think about this. If L2 goes a little closer, this X will be correctly counted, right?
Yeah.
Okay. So it is not contributing unlike other support vectors, right? After that, if line 2 goes here, maybe here, okay, much closer to line L1. Do you realize that, okay, this X is not going to be counted as a support vector, and even the other distances have decreased because L1 will also come down, right?
Yeah.
Okay, so the distances are going to decrease further. So all these points which are on the wrong side, they are also counted as, included in the set of your vectors, support vectors. Okay. So I hope the argument is clear now. So support vectors are typically, so for hard margin, they are the points only on the line. For soft margin, they are the points which are on the incorrect side, and which are on the incorrect side, they are also counted in.
Sandin, can you write it over there for the better understanding? Yeah.
So
because I'm not taking a note today.
Okay. So hard margin is when the vectors that lie on the line. Okay. And support margin includes the points
Which is closer.
which are negatively, wrongly classified. Okay, makes sense?
Yeah.
All right. So we'll see the derivation of these in the probably maybe the second last or the third last session. Okay.
Okay.
Okay. Any other questions about this or anything else that we have studied today or in the previous classes?
Sir, any update on the last Friday's recording session?
See, on that day itself, again, I would urge you to please reach out to your mentors. Okay, don't, treat me as a culprit. See, when you're asking this question, I told you in the last class also, I'm not responsible for that. Okay, so if you keep on asking me again, I cannot help you. I did that on that same day, right? Yes or no?
Yeah, on 10th. Okay, let us.
Yeah, like we have
If you
mailed
want, I can send a reminder again in front of you. Okay.
Let me.
But
yeah,
did you receive any update
Update.
from their side when you messaged?
They reverted and they said that okay, we'll look into it. We'll do the needful. Okay.
Okay, so let's better connect to our coordinators. That way we can find out, I think.
Okay, let me do one thing. Are you able to see the screen, my screen?
Yeah, it was literally like.
Okay.
Yes.
See, if you think that without poking them, if you poke me and they will do it, okay, probably they will not listen to me in comparison to if you poke them. Okay.
Okay.
Okay. See, look at this. This was a video recording that you wanted, right? So she wrote back saying that I'll check. Okay. I wrote to this other lady as well. Her name is Rekha. Okay. She also wrote, okay, she'll check. Okay. Okay, we'll check and update.
Sure. So yeah, let's get in touch with the coordinators then.
Okay. And I'm going to resend a message.
For August 11, yeah.
Okay. Okay, I'll write to Harika as well again. See, again, if you do this, it will have more impact. Me saying it, okay, it's not much.
No, sir, like we have already.
We have also done that. Like
we have not got any response from them. That's it.
Send reminders.
Yeah, like from my side, at least I will say I have done that 2-3 times.
Did you send a reminder? Okay, that's what I'm asking.
Yeah, actually, I totally forgot it. Like today, I'll get in touch with Naveed, which is a main boot coordinator, and
okay. I see again. I'll repeat this. I am not the person who is responsible for managing your data. Okay. Even you can see the drive folder that I'm managing, right? That's my responsibility. I mean, it's their responsibility, but I'm doing it right now.
Okay.
So that is, I mean, I don't want you guys to suffer just because they are kind of procrastinating. So if they procrastinate, it's your responsibility to poke them multiple times. Maybe you can send a reminder on the same day itself. Okay.
Okay. Sure, Santa. We'll get it done by today
Okay.
because
See, I'm not
more persons.
keeping a track of it. Do you know that how many batches do I teach every day? You might not be aware, right?
Yeah.
So I'm teaching in a like throughout the week. I teach around 6 to 7 batches. So for these trivial things, it becomes really difficult for me to keep track of it. That's why I'm telling you again. See, if you need something, you have to poke. Okay. All right. I'm not the right person to poke.
Sure.
Okay.
And Sanatan, what's your qualification actually?
Oh, I have done BTech, MTech, PhD.
PhD.
Yeah.
In
MLD.
which- Oh God. Okay.
Yes.
PhD.
That's okay. I mean, you can do that as well. It's not
Sure.
a big deal.
Yeah. Sure.
I'm not very young. Okay. I'm 33 now.
Okay.
Yeah, I mean, if you're thinking I'm that young, and no. Sorry. Any other things I can help with?
That's all I would say from my side.
Okay. No, I request you to please, I mean, if you have such questions, right, some might take it up in a wrong way. So if you ask the qualifications or credentials of people, right, it is wiser to explore it on your own.
Okay.
I'm telling you as a friend.
Okay, fine.
Yeah, I don't mind it. I don't mind it.
Yeah.
But some other people might have like some other
Okay,
perceptions, right?
Okay.
All right. So
Sure.
she
Because
just
on
sent me a
that-
text. You can
yeah,
see
yeah.
that. Okay, I'll check and update.
Because
Okay.
on that day in a PPT, I've seen like MTech somewhat. So that's
Which
what
which PPT?
I'm not sure. Like in the drive, it was
Oh, that was I am teaching masters and PhD students.
okay.
Okay, so I'm sending you the same slides.
Yeah, okay.
Okay, so those slides are for
that
my
day I've
PhD
seen
students.
it.
Yeah.
Yeah, that day I've seen it. So that's what I was curious. But like I've seen
No, no.
PhD there, so that's what I've asked.
No, that is so. I think you saw it like this. I float a course for my doctoral and master students. I believe you would have seen it like this.
Mm.
Okay, you would see
Slides,
somewhere
I've seen
like
it, I'm not
pre-PhD
sure.
machine learning course. Yeah.
Yeah.
So this is for my students. Okay, 1 second. I believe you would have seen this.
I think so.
Okay. Yeah. So this is for my students. Okay. I'm floating a PhD level course for them. So I just share the material with you guys so that you can also dig deep and learn more.
Okay.
By the way, there is much more in these slides than what I'm teaching you right now.
Okay.
So this is just for your reference sake. I mean, if you want to learn more, you can do that. Okay.
Sure.
Anything else?
Did you get the result for that grid search?
I believe I would have by now. No, it's not doing that well. Okay, it's not doing that well. Maybe because of the randomization in the output code classifier. That could be one reason. Okay, because this also has a random state here. Okay, this also has a random state here. Okay, so currently it is giving me this 89.1448. Okay, but I believe, I mean, if you probably search maybe so currently it was around 2.89, right? So this is still very close to 1670. Okay, just give me a sec. This into 10, it's around 28 models. So it is, it's actually 29, but it's going really high. Could be because of the randomization in zeros and ones. Okay, could be because of the randomization in zeros and ones. Maybe I'll do this. Okay, just a second. Let me check one thing. Yeah, give me a sec. Okay, what I'll do is probably I'll run it, okay, for a little bit longer. and I'll run it for even what we say is more number of. So currently I have 20 values in 1 and 3, right? I am running it in the range of 1 to 3. I'm just using 20 values in between. I will run it probably say for more, maybe say closer to 200 or so. And hopefully you will see that, okay, this should be touched. This should be touched. Even higher than this. Even higher than this. Okay. It is just that like you have to find the right combination between 1 and 3. Okay. So maybe I'm missing like one of the good combinations. All right, I'll do that. Hopefully we'll get good results from this as well. So because 20 values in 1 and 3 will not cover everything. So maybe currently you have the 29 models, right? Okay. So maybe 26 is being missed or 25 is being missed. There you have the best results. And this random state also affects, right? Okay, so these are some of the hyper. So these machine learning models are not free of glitch. Not glitch, maybe dependency on the randomization. So that could be one reason as well for this. But now you at least know. I mean, you can get at least better than this or as good as this as 1 versus 1. Okay. Just a second. When I'm running this. Oh, I got it. Okay. Just a second. I got why we are getting this. Just give me a second. Okay. Let me think. Are these the same data sets that I'm using? So when I'm doing this 5 splits, so around 80% of the data goes here. And here also, how much is that? It's almost 80% only. So here also we have the same stratified waveform. Okay, give me say 10 to 15 minutes. I'll try to run it again. And if we get better results, you will see that here in the Jupyter notebook itself. Okay. I'll try to dig deeper and see if we can reach to that particular value or not. Okay. I'll try it running with some different random states also. Okay. And you'll definitely reach beyond this number. Any other questions? I'll treat random state as a hyperparameter also. Any other questions?
No, sir.
Okay, I'll stop here. I'll upload this file. I mean, after running it, just wait for maybe say half an hour. And let me see if I can reach that particular range as well or not. Yeah. So bye everyone. Take care. We'll meet tomorrow. We do have a class tomorrow, right? Yeah, we do have one. And we'll start with decision trees in the next class. Bye-bye, everyone. Have a good day.
Mm.